In this video, we are going to be discussing section 13.3, which begins on page 866 of your textbook, and the title of this section is Evaluate Trigonometric Functions at Any Angle. So instead of being given triangles like we were in the last couple of sections, or given angles that are the special right triangles, 45, 45, 90, or a 30, 60, 90, they're not going to be these nice angles. So we need to learn how to manage and deal with them. So the very first thing we need to discuss are general definitions here. So if we look at this circle, this is going to be referenced as the unit circle. Here we don't know that it's a unit circle because we don't know that the radius is 1. The radius could be anything here. So let theta be the angle in standard position. Alright, and let x and y be some point. So they're going to give me any point, so I'm going to go x in the left-right direction here in the horizontal direction, and y in the up-down vertical direction. Alright, so that by giving me a point, they're giving me two sides of a triangle, and then the third side is going to be my radius there, and the distance between the origin and the circle that I can draw. Alright, so the 6 trig functions are still going to be referenced as ratios here. So instead of being opposite over hypotenuse, we need to think of it as y over r for sine, and then cosecant would be r over y, cosine is going to be x over r, and then the tangent is sine divided by cosine, or y divided by x, and the cotangent is going to be the reciprocal of that. Right? These functions are sometimes called circular functions. I'm going to be honest, I haven't in my career in mathematics, I rarely, if ever, hear people refer to these as circular functions. Alright, so looking at example 1, I am given a point, -4, 3, and let that be a point on a terminal side of the angle in standard position. So evaluate the 6 trig functions. So what I want to do is I want to go ahead and draw out this triangle a little bit bigger, just so you can see it for a second. Alright, so here is the origin, and theta is this angle. Alright, so no matter what that angle is, we're going to evaluate sine, cosine, tangent, cosecant, secant, and cotangent. So if I went to the left, -4, and then up 3, this is what the triangle looks like, and then I need to find my third side. So, solution, we need to use the Pythagorean theorem to find the value of r. So, using x squared plus y squared, and then taking the square root of that, that should give me my hypotenuse here. So, -4 squared is a positive 16, and then I add 9 to that, and I get 25. Square root of 25 is 5. So maybe when I originally drew that, and I had set it up, you saw that it was a 3, 4, 5 right triangle. Alright, except here, instead of a positive 4, it was a -4. So using these values, we can write all of these functions. So sine, being y over r, is 3 over 5. Cosine, x over r, is negative. It is going to be negative 4/5. Tangent is -3 over 4. And then all I need to do here for the next 3 is take the reciprocal of their corresponding functions. So cosecant ends up being 5/3. Secant is -5/4, and cotangent is -4/3. Alright, so you might have a question popping in your head, how do I know whether it's going to come out positive or negative? And as you can see, I only have one negative value here, and that's with x, so it depends on whether you're using x or not. And it's also going to matter which quadrant this angle falls in. So the fact that it was -4, 3 was the point that we were using, that had an impact. So we're going to be looking at a couple of these differences here in the future. Alright, so the unit circle, that's what I had referenced here, is when the radius is 1. Alright, this is a very typical value that we are going to be using, especially in pre-calculus. Alright, so x squared plus y squared, that's my circle, and the radius of 1. So the center is still at 0, 0, and in this case, sine of theta is y over r, or y over 1, which is just y, and cosine in the same respects is just going to be x. So whatever your point is, if it is x comma y, another way to write that is cosine of theta comma sine theta. Alright, and how I remember that is if it falls on the unit circle, I always think C comes before S in the alphabet, so at any point xy is the same as cosine comma sine, so whatever those values are in the point, those are my cosine and sine values. And then I can find tangent by taking sine divided by cosine, and I can then find the other three trig functions by taking the reciprocal. Alright, so the unit circle is a beautiful thing. Alright, and it is convenient to use the unit circle to find the trig functions of quadrantal angles. Alright, quadrantal angles means that they are going to fall on the axes. So if I look at these axes, a quadrantal angle means they're going to fall on these points. Alright, and if I look at these points, this is going to be 0, 0, comma 1 if it falls on this unit circle, alright, with a radius of 1. This is going to be negative 1, comma 0. This is going to be 0, comma negative 1. And this is going to be 1, comma 0. Just looking at one of the points here for a quadrantal angle, if I've got negative 1, 0, so that would be, keep in mind that's 180 degrees, alright, from standard position. So the cosine of 180 degrees, or the cosine of pi, is going to be equal to negative 1, and the sine of 180 degrees, or the sine of pi, is going to be equal to 0. Alright, and then in order to find the tangent, I'll just write tangent of pi. Tangent of pi is sine over cosine, so 0 over negative 1, or 0. So just by, drawing out a quick picture, drawing out these points, and memorizing the relationships between these trig functions, you're going to be able to construct these examples fairly easily. So let's look at an example. Use the unit circle to evaluate the 6 trig functions for theta equals 270 degrees. Alright, so if I were to draw out in standard position, starting on my x-axis, and then continuing around, I get to 90, 180, and then another 90 degrees is 270. Alright, and so it falls exactly on the point 0, negative 1. So setting it up, sine of theta is going to be negative 1, and then the cosecant is also going to be negative 1. Alright, and as I said before, we can think of this as cosine comma sine of that angle. So I could have easily just jumped straight in towards the negative 1. And then in order to find the cosine, I would know that it is 0. The problem arises when I find the secant is when I do take the reciprocal and I do 1 over 0, it is undefined. Alright, we are going to get some undefined values, and if we look at these graphs in the future, you'd be able to see why. Alright, so then setting up tangent, if I do the sine over the cosine, negative 1 over 0, that's going to give me another undefined value, but this time if I do it the opposite way, I do cosine over sine, take the reciprocal of that, 0 over negative 1 is 0. Alright, and we should be able to then set up all these x's and y's. If you have just these two memorized, you can construct the other ones. Alright, so why don't you guys go ahead and try out a guided practice, pause the video, and then some solutions will pop up in a second. Alright, so if you guys have any questions on how to construct these, the third side here, our radius, or one of our sides for the point, it may not be even. So that might be the tricky part, and we always have to remember to rationalize our denominator. Alright, that's where these radicals are coming from. So for these reference angles, we're going to try to use these radicals, these reduced radicals, as much as we possibly can, writing them in simplest form, and we're going to try to avoid using decimals and rounding, because as you know, rounding burns bridges and people die. Alright, so let's try out guided practice number 2. Pause the video, see if you can get what we get. And in this example, it does come out nice and even where the radius is 17. So this is a Pythagorean triple. And do notice that depending on the quadrant it falls into, some values are negative, while others are not. Alright, and on this slide, it is rearranged in a little bit of a different order than it was before. So just keep that in mind. Cosine is second here instead of cosecant, so please don't get confused if it's just in a different order. Alright, and guided practice number 3. And again, my radius comes out evenly, so this is a nice example of another Pythagorean triple. Alright, and it is going to fall in the third quadrant. So some different values are going to be negative instead. Alright, and last guided practice here. Use the unit circle to evaluate the 6 trig functions of theta. Alright, so if I were to draw out my lovely unit circle here, I know that 180 degrees would fall on this point, -1, 0. So then this is the cosine, this is the sine. Alright, or if you were to set it up using your x's, y's, and r's, you should be able to set it up nice and easily, and you will have some undefined values due to having that 0 in the denominator. Alright, reference angles. So a reference angle is just an angle that's going to allow us to draw that smaller triangle instead of having to use a larger theta or a larger angle. The reference angle is going to be an angle between 0 degrees and 90 degrees, or 0 pi radians and pi over 2 radians. Alright, so it's going to be an acute angle that we can use to draw a triangle. So if you were to look at this picture, if I were to use this point, I can draw a nice triangle back to my horizontal x-axis here, right? And then the angle that we're going to be talking about is this little theta between my terminal side here and that x-axis. Alright, so it's just allowing us to use a triangle idea instead of having to mess with a larger angle. Alright, so these reference angles are very helpful. So how do we get these reference angles? Quite simple. If my angle is in quadrant 2, which by the way, we start in quadrant 2 because if my terminal side is in quadrant 1, my reference angle is the angle I have anyways. Alright, so if my reference angle is in number 2, quadrant number 2, I draw it back, and I just take it away from 180 degrees in order to get my reference angle, which we're going to call theta prime, as you can see over here in the reading. And if my terminal side is in quadrant 3, draw it back to the x-axis, and yet again, I'm going to take theta here, and instead of taking it away from 180, I'm going to take 180, or pi, away from theta, depending whether it's in degrees or radians. And then if it's in the terminal side is in the 4th quadrant, I'm going to take it away from 360 degrees, or 2 pi. So let's look at an example. Find the reference angle for theta prime if theta is 5 pi over 3. So first I need to figure out which quadrant that is in. Alright, terminal side lies in the 4th quadrant, and how I determine that is, for me, what I do is I simply draw out my little picture, and I have that at the top of my page. I know that this is pi over 2, or 90 degrees. I know that this is pi, or 180 degrees. And I know that this is 3 pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2, or 270 degrees. And I've got 0 and 2 pi, or 360 degrees. Okay, so I just figure out which values it falls between. So it is in the 4th quadrant. So I take it away from 2 pi, and my reference angle here is going to be pi over 3. And I do the same thing, however this time it is negative 130 degrees. So if I'm moving negative 130, I'm going to lie in quadrant 3. And theta prime, so what I need to do is take 180 degrees away from 230 degrees, then add 50. So you might be questioning, where did that 230 degrees come from? So first I'm going to go ahead and draw out what it means to be negative 130 degrees. So this is negative 90. And then if I go 40 past that, alright, so here's my terminal side here. This is negative 130 degrees. So they say a coterminal angle is positive 230 degrees. Alright, so that completes the circle. So that's where the 230 came from. Now the question is why did they do it? And right here is why. Alright, so we are going to want to deal with angles in standard position, and we want them to have that positive value. So if I do have a negative angle, I am going to want to use a positive coterminal angle to find the reference angle. Alright, so since it did fall in the 3rd quadrant, I took 180 away from 230 degrees, and that should be an equal sign. I apologize. Alright, should be an equal sign instead of plus 50. So if you did notice, you might have been able to piece it together. You are going clockwise 130 degrees, which means it is going to take you an additional 50 to get back to that axis here. So whichever way you figured that out, should be alright. We are going to try to consistently use these 3 ways, depending on which quadrant we're falling into. Alright, so evaluating a trig function. So one of the questions that we asked before was, how do I figure out whether, my sine, cosine, tangent, cosecant, secant, or cotangent is going to be positive? So they have this lovely chart in your book. This is not how I learned it, however. I learned it with a little abbreviation, and it was all students take calculus. All students take calculus. Now you might be able to think of another way to memorize it, or another saying here, but that is how I memorized it. So all students take calculus. So you're starting in quadrant 1, going to quadrant 4. So what that means is in the first quadrant, all of the values are going to be positive, all right? We love positive values, so that's kind of what we're going for. So all are going to be positive. Here in the second quadrant, students starts with an S, so we want to think of sign, all right? So the sign is going to be the only one that is positive, and its corresponding reciprocal trig function, the cosecant. All right, here in the third quadrant, T stands for tangent. Tangent's going to be positive, and its corresponding trig reciprocal, cotangent as well. And then in the last quadrant, cosine is going to be positive, as well as secant. So if you can memorize all students take calculus, you should be able to figure out whether it's going to be positive or negative, depending on which quadrant it falls into. So let's look at an example. The tangent of negative 240 degrees. All right, so if I just draw out a simple example here of negative 240 degrees, I go past 180 and I go 60 degrees past 180 clockwise to get negative 240. So my reference angle here is going to be 60 degrees. The part that they didn't show you is finding the coterminal angle in the picture, which is 120 degrees. All right, and the tangent is going to be negative, so if all students take calculus, so sine's the only one that's positive, as well as cosecant here. All right, so that means tangent is going to be negative, and then I can find the tangent of 60 degrees. All right, I know that the tangent of 60 degrees, memorized off of that chart from section 13.1, is, so if I were to write it out, tangent of 60 degrees equals square root of 3. And since the angle that we have is negative and it's in the second quadrant here, we need to make sure that that is negative as well. So it ends up being a negative radical 3. So let's look at part B here. So the angle 17 pi over 6 is coterminal, so what I'm going to do is take that 17 pi and I'm going to subtract, that seems pretty large to me, I'm going to subtract 2 pi. Alright, so when I do 17 pi over 6 minus 2 pi, I need to find that common denominator. 17 pi over 6 minus 12 pi over 6, and that's how they get the 5 pi over 6 as the coterminal angle. So as far as logically figuring out which quadrant this is going to fall into, look at that 5/6. Alright, so I know that I'm dealing mainly with, pi over 2, pi, or 2 pi, and then 3 pi over 2. So keep in mind that this is 1/2. Alright, and from pi 1/2 pi, this is 1 pi, this is 3/2 pi, and 2 pi. Alright, so 5/6 is larger than 1/2, but it is less than 1, so I know that it is going to fall into the second quadrant again. So if I were to look at all students take calculus, I know that the sign is going to be positive, so that makes the cosecant positive as well. So the cosecant of 17 pi over 6 is the exact same, it is going to be positive, as the cosecant of 5 pi over 6, which is going to equal 2. Alright, so sketch the angle and find the reference angle. Here's some guide practice. Feel free to pause the video and some solutions will pop up in a couple of seconds. Alright, so on this guided practice, 15 pi over 4, if I were to write that as a mixed fraction here, which is a mixed number, absolutely disgusting, alright, completely detest this, but it might help you think about it. So, if I look at the picture to the right, starting in standard position, when I go from here to here, that is pi, moving an additional pi, so that's 2 pi, and then I hit here and that becomes 3 pi. Alright, so then I need to go an additional 3/4 pi, so I'm going 3/4 of the way, and that's how I get to 15 pi over 4. Alright, just wanted to throw that out there as another way of tackling this problem. Alright, so we evaluate that. The coterminal angle is pi over 4. Alright, so here in example 5, calculate the horizontal distance traveled. So the Frogbot is a robot designed for exploring rough terrain on other planets. It can jump at a 45-degree angle with an initial speed of 16 feet per second. Alright, and on Earth, the horizontal distance traveled is d in feet, traveled by the projectile launched, at an angle theta with initial speed v. Alright, so that is given by this formula. All to say, we are going to be using this formula. And I have a feeling, like if you are looking at a word problem and they say something about initial speed or horizontal distance, you're probably going to need to reference back to this formula. So, solution here. What we need to do is fill in these values. So I have an angle right here, as well as initial speed of 16 feet per second. So I only have two variables in which I need to fill in, and that is theta and v here. So filling in 45 degrees for theta and 16 for my v here, my velocity, my speed. I simplify that. So you can type all of this in one step, one go around. I would just be careful and make sure that, let me clear this out. When you do that, so typing it all in, I use some parentheses here. So I'm going to have 16 squared divided by 32. Close that in its own set, and then I'm going to have the sine of 2 times 45, or you might just know that that's 90. Alright, and so looking at that, you can then press enter, and that should give you 8. Alright, as long as you are in the correct mode. So please do keep in mind that if you're dealing with degrees, your mode, so how I get there, on this calculator is I press mode and then I need to arrow down. I was in degrees, but if you're seeing pies, you need to make sure that you press enter in radians. So depending on your calculator, it might be a little different. Alright, so the Frogbot can jump a horizontal distance of 8 feet. Alright, and then we have this lovely rock climbing example, which I'll give you a second to read. So this whole question is looking for how high above the ground. So we are looking for this y value here. Alright, so this is going to act as my origin. Alright, because that is the center of rotation. Alright, so we need to find, I guess right here, we're just going to need to find this y value first, and then we can add on the additional 6 feet at the end. So we're going to be using sine here. The reason we are using sine is because if you draw this triangle, like I said, so we have this point, Alright, we have this point right here at the end. If you were to draw this triangle back to the horizontal axis, what we want is this y value. So if I were to look at theta, or its reference angle, theta prime, and I were to do the sine of theta prime, that's going to be equal to y over that 5.25. Alright, so if we set that up using the definition of sine, filling in my angle here, sine of 110 degrees is going to equal y over 5.25. And evaluating that by multiplying each side by 5.25. 5.25, making sure that my calculator is in degree mode, I should get y approximately equals 4.9. So from that step, I just need to add on the vertical distance there of the 6 feet, recalling. So I just found this was about 4.9, so I need to add on the additional 6 feet, which is segment addition. And that's going to give me a total of 10.9 feet above the ground. Alright, looking at another example here, track and field. Estimate a horizontal distance traveled by a track long jumper who jumps at an angle of 20 degrees with an initial speed. So like I said before, we're going to need to use that formula in one of the previous examples. And here is that formula. So I need to fill in my velocity and my angle, making sure that since it's in degrees, I have it in the correct mode on my calculator. And 27 fills in for my velocity, and then 20 fills in for my angle. So 27 feet and 20 degrees. I evaluate that, and I get about 14.64. Alright, so our final answer here is the long jumper can jump 14.64 feet. So that's your last guide practice. Alright, what if in example 6, how high is the top of the rock climbing treadmill if it's rotated 100 degrees instead of 110? So if I go back, alright, if it's rotated 100 degrees, I assume it's going to be a little bit higher. I don't know, once you find out. And if you do all of the math correctly, it is going to be 11.2 feet. So my guess here of it being a little bit higher was correct. Alright, if you guys have any questions, always feel free to send me an email or make a comment on Google Classroom. Good luck.